An awesome place. So I had a lovely time. While I've been there, Mania, and I'm going to go and pick them up from the airport this afternoon. So I won't hang back a long time after today's lecture, if that's okay. And unfortunately, it means I missed the sumo thing, which is very sad. They will record it and I'll watch it on movies. But I would have liked to come along and support you guys in the sumo comp. But so anyway, just while I was in fact giving the last lecture, I began to feel quite nauseous. Nothing to do with you guys or the content of the lecture. And then I got incredibly sick, sicker than I can remember ever being before. And I was pumped up with all sorts of drugs and things. And I still went to Hong Kong and hopefully haven't started another SARS equivalent. And it meant there were a couple of things I wanted to do before I left that I didn't get to do. So let me try and catch up with those things now. You'll notice, I hope, that I've been putting up tute and lab solutions furiously in the background since I've been back. So there's lots more tutes and labs up, and I hope by the end of this week to get them all up, so everything's caught up. And I also hope to put up a page or a series of self-test exercises and a little tutorial for those who are still not completely happy with the machine code, just so everyone gets up to speed on that. Because at the end of this week, I would like everyone to be up to speed with machine code. Now let me just connect. I think everything's working now. I had enormous pleasure on the weekend, or on Sunday, after I got back, looking at Tim's lectures. And it was amazing. What a good consequence of being able to video the lectures. I was able to see exactly what he did. How's that? Oh, it's a bit dark. Is that too dark? Oh, this is this hard line. Ah, yeah. Ah. Oh. Technology's working. Thank you. And last step, connect to the internet. So I was able to see everything that happened. So I'd like to start today's lecture with a little bit of revision. Because one advantage I had being able to watch the lectures was I could watch you guys be moving and being restless, and I could work out what bits you got and what bits you didn't get. It's really good. In fact, I'm proposing next year that we wire students up with electrodes so the lecturer can see this information. So it looked to me like all the Monday stuff went perfectly well and was absolutely brilliant and fantastic. And on the Wednesday, it looked like a lot of people got a little bit stressed. I could sense stress in the first 20 minutes of the lecture when pointers were being done and that swap piece of code was run and things like that. So I thought I'd just touch on some of that again. Oh, now why can't that page be displayed? That's not good. Perhaps if I use Firefox. There we go. And oh, I am logged in. Oh, I forgot to log out. It's been logged in all this time. Oh, where's... Oh. There we are. Here's today's lecture. So, first of all, my plan is approximately to spend the first half of today's double lectures revising pointers and address of, and talk about a couple of interesting issues that rise up. Then I plan to show you a magic trick, which will be fun. Then I plan to tell you something interesting about estimation. And then I'm hoping that we'll spend the second half of today doing a worked example using arrays and also talking about the task 2. So that's our plan for today. Now the key, I think, behind the whole pointer thing is this issue that I know I keep going on about, but let me just go on about one more time. The distinction between talking about something, literally itself, and talking about a reference to something. The old toilet sign. Yep, a toilet sign is not the toilet. So if we just go to the 4-bit machine code for a second and assume we've got 16 addresses and they're labelled 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We've got 16 memory cells and they all have an address. And the address is a number. Each memory cell can also have contents. I wish I had more colours. All right. I'll do it in different fonts. How about that? The contents are also numbers, say, between 0 and 15. So the contents might be 7, 2, 4, 8, 11, 10, 3, 5, 10, 8, 2, 6, 1, 0, 0, 5. Can everyone see that every cell has an address and a value? Now, normally when we talk about things, it's clear which we mean, so we just unconsciously disambiguate which of those we're talking about, and everything makes sense. But I'd like us to pay explicit attention to it, because sometimes that disambiguation you can't do explicitly. You can't do unconsciously, you've got to do it explicitly. So let's, for example, pick this cell here and say that in this cell here, which has address 10 and has value 2, this cell here, suppose I'm going to call that x. And on this system, x is an int. And ints on this system store numbers between 0 and 15. So whenever I'm talking about x, I mean this cell. What do I normally mean when I say x? If I say tell me x, what do I normally want you to tell me?
The value.
Yeah, normally when you say a name, that's correct. When you say a name, normally you mean the value. That's the normal thing you mean. In C, it's exactly the same. A variable corresponds to an address in a location in memory. An address corresponds to a location in memory. A name corresponds to a location, a cell in memory. Finally managed to say that right. So when you say x in a C program, and x has previously been declared as an int, when you say x, you normally mean the value stored in this location. So x normally means the value of that cell. If I wanted to talk about the address of that cell, how do I disambiguate that in C? How do I force C to tell me the address of the cell? Not star. Ampersand. Ah. I can do it. I'm actually going to do an ampersand today. Today's going to be my first day I've done an ampersand. I knew I could do it. I knew I could do it. Ampersand x means the address of x. X means the value of x. You must burn this into your brain. Now, this isn't too hard to understand. But sometimes when we want to talk about a cell, we haven't given it a name. If we've given it a name, everything's easy, and we can just refer to the cell by the name. But sometimes we haven't given it a name. How else can I refer to this cell? Suppose I wanted to refer to this cell here, which happens to have the name Y, but suppose I didn't know that, and I wanted to refer to this cell. How could I refer to it without its name? Yes? I could say, I'll say it in English first. That's dead right what you said. I'll say it in English first. I'd say the cell at address 7. And to make that short, in C we write star 7. Now, so Y and star 7 are really the same. Can you see? They're just different names for the same cell. And when I say star 7, do I mean the address of this cell, or do I mean the value of this cell? The value, because that's our default. When I talk about a cell, I normally just mean its value. So star 7 means the value of this cell. So if I said to printf %d, what am I trying to say? Star 7, what would it print out? It would print out a 5. Now you might ask yourself, why bother? Why don't we just use names for everything? Why do we want to be able to talk about things without using their names? Talking about something without using its name in this way means we're not talking about it directly, we're talking about it indirectly. And it's called indirect addressing. So when I talk about indirect addressing, I mean I'm referring to something without giving its name. So I could use indirect addressing here. I could say, the person sitting 3 rows back, 2 seats in. What is your name? Chan. Chan? C-H? Chan. Okay. I've specified that seat. And I mean the value of that seat, which will be, say, the person sitting on it, because that's the default. When I talk about a cell, I mean the value. So I'm meaning the value of Chan. But I didn't have to say Chan's name because I referred to that location in a more roundabout way. That's indirect addressing. I could put a number on every single seat. And I could say the person sitting at seat 57. I'd be indirectly addressing, say, you. What's your name? Ritika. I'd be indirectly addressing Ritika. I could address her directly by saying Ritika, or I could say, hey, the person sitting at 67. Or I could just say, hey, you. That's favourite lecturer speak. We prefer indirect addressing. You! Out of my room! But it's Theo, I know that. Yes?
If you don't initialize a seat, is there rubbish in it?
Oh, if you don't initialize anything anywhere, there's normally rubbish in it. And maybe the compiler's clever and fills default values in, but should we rely on that? No way. And even if we know the compiler does that, should we rely on that? No way. Never just assume things will magically work. Let's make them explicit. Unless there's a huge cost in it, let's make it explicit. So you now know how to use a star, hopefully, and you know how to use an ampersand. What if I was to say this? Printf, ba 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 ba, star x. What does that mean? Tell me what you think it will print out. No, you think it yourself. Don't call it out. Well, no, we're using this example over here. Okay. How does C interpret this? C is so, once you understand how C does things, it follows the same rules every day. There's no mystery about it. So we just have to know the rules and we can work everything out. Star is an operator. So we've got an expression here. The operator is applying to a value. We have to evaluate the value first. What does X mean? When we say X in C, what's that shorthand for? The value stored at X. Remember, that's what we mean. When we say the name, we mean the value stored. That's the default. Before it was obvious, it's a bit less obvious now. So thank heavens we made it clear. What is the value stored at X? This was X, so the value stored at X is 2. So this is really saying what? Star 2. What is star 2? 4. Address number 2 contains the value of 4. So this would print a 4. That's it. It's no more complicated than that. That's complicated, but that's as complicated as it is. So if you understood what I said and you write good notes about it and you just burn it into your brain and try lots and lots of examples, you now understand everything you need to know about pointers. Tim did talk about pointer arithmetic. We're not going to do pointer arithmetic in this course. Pointer arithmetic, read backwards, sounds like country and western music. So we're just not going to do it. Okay. Yes?
You know, it prints out 4. What if you just put an X there? Wouldn't it print out 4 as well?
If I put an X there, no, if I, yeah. What would it print out if instead of printing out, I'm going to do a separate example down below, but I'm going to be lazy. Comma, X. What would that print out? Well, this is going to print out X. When I talk about X, what do I always mean when I say X? The value of X. What's the value of X? 2. What if I said print out comma effortlessly X. What's that going to print out? 10. Now here's a hard one for you. This is homework. If I said print out star ampersand, 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 star, star, star x, what am I talking about? It's a number. We're just going to have to work it out. I'm not sure how C parenthesizes these things, so let's put the parentheses in explicitly. Look, this looks like an incredible exam question. This is definitely going to be an exam question. All right, so let's work it out. Well, shall we work out this ridiculous exam question? Yes. All right, what's x? 2. All right, what's star x? X is 2. Let's double check that. Yes. Star x means what's stored at address 2, which is 4. All right, so this is 4. So what's star 4? Thank you. What's star 11? Oh, let's just check that. Star 11, I should check it, is 6, isn't it? Okay. Star 11 is 6. What's the address of 6? It's 6, isn't it? No, this is saying, what's the address of this number? Oh, heck, I don't even know where that number's well. Oh, bloody hell. That's confusing. It looks to me like maybe it only makes sense if you put the ampersands first and then the stars second. I think try it out. Try it and see. Okay, we've now moved into territory that's freaking me out a bit. It's not going to do a magic trick. It's not going to search through memory trying to find where 6 is and return its address. See, it doesn't do any work. It's comparatively lazy. It wants to know the address of this 6. This 6 is in the middle of an expression, so I don't even know that it has an address. So it's probably just rubbish. So it's a rubbish exam question. So when you see this question in the exam, just write rubbish all over it. And anyone that tries to answer it will waste hours and hours and hours and hours, and you'll be well ahead of them. Okay, does everyone understand all of that? Are there any questions about addresses and pointers and values? Yeah. Oh, you haven't seen a practical use? Oh, yeah. Look, I like you. What's your name? William. William asked a really good... have I spoken to you before, William? What's your surname? Chen or something? Sue. Okay. I recognise your face. Suddenly it came to me. William's asking a really key question, which we should always be asking, which is, what's the point of learning all this? If I could rephrase that, I think the really good question to be asking here, or a really good question to be asking here is, what's the point of indirect addressing? I cannot see any value in indirect addressing. Hang on a second, William. When everyone's on top of indirect addressing, oh, we can do something wonderful with it right away, in fact. I'll do something wonderful. A, we'll do something wonderful right now. But B, there's something even more, in fact, more wonderful things we'll see that we can do with it that occur later in this course. In fact, most of the really wonderful ideas in the course are going to need to be able to do this indirectness in addressing. Are there any more questions about pointers and addresses? Okay. Let's look at number 1. I said there were three things. Let's look at number 1 for a really neat thing to do with pointers and addresses. And it's this, and Tim's sort of said this already. But hey, shh. Is that muttering, is that good muttering? Are you explaining pointers and addresses to each other? Or is that bad muttering and you're doubling and doubling and doubling and trying to work out how many Mars bars I owe you? Look, if everyone, how many do I owe you? 256. It cannot be 256. Because there was, like in week 1, I promised it on the first day, didn't I? And I promised I would deliver it on the second day. When I didn't deliver it on the second day, I owed you 2. And then we had week 2, then we had week 3, then we had week 4, we had week 5. I couldn't have delivered in week 5, so you can't penalise me for that. I only get penalised when I forget to bring it along. So 1, 2, 4, 8, 16, 32, 16, 8. What is that? 64. Oh, we're only here now. Oh. My sleight of hand didn't trick you very much. That's week 1, week 2, week 3, week 4, week 5, which doesn't count now, week 6. So we go 1, 2, 4, 8, 16, 32, 64, 128. So am I right in thinking next week I'll owe you 1,000? And by the end of the course I'll owe 1,000,000? This is the amazing power of doubling. That is astonishing. Well, okay, let's just erase this very quickly and move on. Look, the thing that Tim pointed out at the end of the lecture is really the key first use of pointer as in C. When I have a function, I'm running my main function. I'm going to draw a picture of memory, okay? When I'm running my main function, the code's up here, right? And it's probably storing all its data in a stack in a frame down here, low in memory. And if the main function calls another function whose code is up here, it's going to be storing its data somewhere, maybe down here, maybe above it. Oh, actually, let's say it's above it, because that's more likely to be where it's stored. And that's my sub function. What does that do? That does something. Who knows what it does? It does some task. Task stores its stuff in here. Now, I've said before, one of the really neat things about functions is this notion of scope. This wall, abstraction of wall around them that stops, while main's being executed, it can't fool around with any of the variables of task. And when the subtask's being executed, it can't fool around with any of the variables of main. It can't because all their data is stored in their frame, and that's the only data they're allowed to use. It's the only data they know about. Now, let's suppose that there was a really good reason for task to fool around with some of main's data. Notice I'm not saying there is a really good reason. We'll have to later on think, gee, is this a really good thing to do? Under what circumstances? Hey, people talking. Shh, 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 shh. But suppose that task did want to fool around with main's data. How does main communicate with task? Well, suppose main calls task and it's got two variables, x and y, and they're both ints, and it passes them in. What happens when main calls task? What happens to the values of x and y? Suppose x stored the value 10 and y stored the value 100. It copies them. So these x and y, who are stored somewhere in here, x and y, which stores 10 and 100, are copied into here, 10 and 100. And in here you might have given them the same names, x and y, or you might give them some other name, and hopefully by now you've worked out it doesn't matter what name you give them, they're separate. And if you fooled around with the values inside task, is it affecting main at all? No. So what's so far the only way task has of communicating back with main? A return value. At the end of task, at the end of the code for task, it'll say something like return 0. And that value gets passed back to main. So far the only way of task sending data to main is by returning that data. And that's really good for a number of reasons. But suppose we wanted to break that. Suppose we wanted task to be able to fool around with main's data directly. Suppose we want a task to be able to get to x and y here and actually swap them round inside the memory here. Or suppose we wanted it to be able to just take these values and change some of them mysteriously. So when the function returns, main has been altered in some way. This is clearly what? What do we describe this sort of behaviour as being? Someone said it. What was it? No, it's not necessarily bad, but it's usually bad. It rhymes with ride abrecht. What could it be? Something that rhymes with ride abrecht. Hide my Brecht. I've got a book of Brecht. It's a hint. It rhymes with side effect, the phrase I'm looking for. Side effect. Thank you very much. It's a side effect. If calling task, in addition to returning something, fools around with main, task has a side effect. And remember, for various reasons that I hope I've explained up until now, and if I haven't, grill me before the end of the course, side effects are normally seen as being really bad. But suppose we wanted to have a side effect. Suppose we wanted task to be able to fool around with main stuff. How can it? It appears impossible. But no longer is it impossible. Someone that knows, tell me. Put up your hand. Wave at me. How? How? No, no, you on the end. Pointers. Pointers. How could you use pointers? You've got a Google chat on. So, we can't have Google in here. This is private. Nothing between these walls ever leaves these walls. Oh, you've... So, how can we use pointers to let task fool around with main?
Well, the variables in main are stored in memory.
The variables in main are stored in memory. Yeah, they're stored inside main's frame.
At locations. And so
At locations, say, 1092, 1093. Yep.
And so task can access those locations.
How can task access those locations? It doesn't know where those locations are.
Because you can pass the location.
Who can tell it where those locations are? Main. So when main calls task, if main, instead of giving task some information that was like copied values, if main told task the address of some of its own secret locations, task can go to those addresses. Suppose task looks like this. Suppose task gets passed in an x, no, we won't say an x and a y. Suppose task gets passed in P1 and P2. And suppose they're the addresses of x and y. If task wanted to fool around with those addresses, how would it refer to them? It doesn't know the names x and y. They're not in its scope. But how can it refer to those cells?
Star P1, star P2.
If it talked about star P1, it's really talking about x. If main passes in x and y. Oh, if main passes, what would main have to pass in? The address of x, the address of y. If main passes in the address of x and the address of y, task can access those cells by calling them star P1 and star P2. Does that make sense? Okay. This is neat thing number one about pointers. Does that convince you a little bit, William? Yeah, yeah. It lets you fool around with memory inside someone else's stack frame. Now, whether that's good or bad, that's a separate issue. All right, so we've done. And when you can change things like this, in some languages it's called a var parameter. The things you're passing in can be changed. And C, we don't call it that. But if you programmed in Pascal, this is a var parameter. Yes?
How do you use that? Do you use when you're calling the task function?
Yes?
Do you put star P1?
Ah, yeah. How do you actually call it? Well, actually, maybe you can tell me. I reckon you can work it out. I'm inside main. In main, blah, blah, blah. I'm just about to call task. And I want to let it fool around with my x and y. I've got an int x. I've got an int y. I want to let task fool around with it. I go task. What do I have to pass into it? What does it need? What does task need to know? Got it. How do I write the address of x? How do I write the address of y? You got it. So when we pass it in, we pass in the addresses. Now we're in task. Task is void. Doesn't seem to do anything. So void task. Here are its parameters. What's it expecting? It's not expecting ints. What are you giving it? Addresses of ints. Do you remember how we say that? We say int star P1. Int star P2. That's how we tell it where it's expecting pointers. We're passing in addresses. Those addresses we also call pointers. In C we read this, it's like a little game. Star P1 is an x, is an int, this says. Star P1 is an int. You guys told me before what star P1 is. What's star P1? No. P1 is the address of x. So star P1 is x itself. Yeah, is x. And what type is x? An int. So star P1 is an int. So that's right. The contents of the address of P1 is an int. And this is what we're telling it. In other languages, you write it like this. Int star P1. You say P1 is a pointer to an int. But in C, we don't say that. We say the thing that P1 points to is an int. We put the space in a different spot. You could put the space here. You could put the space here. C is going to forgive you if you put it in the wrong spot, but don't. It'll forgive you in small examples. In more longer or complicated examples, you can actually trip yourself up if you put it in the wrong spot. So star P1 means this is an address of something. This is the contents of that address, which is an int, which is an int, which is an int. That's what we're saying. Does that make sense? Does that answer your question? And inside the code down here, whenever we want to refer to x, what do we have to say? Star P1. So if I wanted to increase x by 1, what would I have to say? Something like star P1 equals, oh yeah, I could do plus plus, but let's do star P1 plus 1. Let's do it like that first. Now this is a rare example in C where it allows you to put an operator on the left-hand side. It really just regards these two things as talking about a single memory location. Normally all the operators have to go over here. Now we could say star P1 plus plus. Now what are we relying on? Yeah, we're relying to the fact that this operation gets called, here are two operations being applied to this value. We're relying on, yeah, we rely on this all over the place. We rely on the fact that this happens first and then this happens second. If it happened the other way around, we'd be in the poo, can you see? If it increased the pointer by 1 first and then found what was there, instead of increasing x by 1, it would return the value at whatever 1 after x, which is y. Terribly confusing. Anyway, luckily C does it that way, and that's sort of an idiom. No, it doesn't? Oh, it does it the other way?
I got a bug when I tried that.
Oh, well done. Cool. So, but for me, I like putting things in brackets because even when I think I've got it right, sometimes I've got it wrong. Yeah. In brackets, it does the right thing. So here, yeah, we're assuming this has high precedence in the plus 1. That's probably okay, but you could put it in brackets if you wanted. Okay. Yes.
How do you pass that back to main?
You don't have to pass it back to main. If you wanted to pass something back, you'd say return, but we don't have to. What we're saying here is go to the address that P1 points to. Yeah, so this is literally talking about the X that's hiding inside main. And it's directly operating on that address. So when it finishes, that's why we called it a void, it doesn't actually return anything. It's already done its evil work. You know, normally a function does its work and then says, and here's the output. But you say, do some work. She goes away, and I say, have you finished? She said, yeah, man, I did it a long time ago. Well, you were still talking to me. Okay, that's what happened. It's happening in the middle. It's updating while it's running. Makes programs much harder to analyze mathematically, which is one of the reasons that it's slightly frowned upon. And it's not only harder to analyze mathematically, it's harder for us to see what's going on. It allows more interactions. It makes things more confusing. Confusion is always bad in a program. There's always enough confusion inherent in the problem. We don't need to add more in the particular way we solve it. So we normally strive to minimize confusion. So side effects tending to be more confusing are often avoided wherever possible, usually avoided wherever possible. Okay, so you've seen now, A, how we use star and how we use ampersand. B, a good example of why it's neat, because this lets us change things. And from inside one function, we can change things inside another, which essentially lets us return more than one thing at a time. You might be itching to return 2 things from a function. Up until now, we've only been able to return 1. Now we can have a function affecting as many, 50 cells or 60 cells of memory. Can affect as many as at once using pointers. Both a blessing and a curse, because the more powerful you make functions, the more chance that they can stuff up. Okay, so we pass by reference, how we do it, why we do it. Okay, I've just said why it's bad about it, but people still do it. What's good about it? What's good about, oh, did I say one's passing by reference, one's passing by Firefox is ready to install? Let's just, okay. Pass by value is what we normally do in C. That's when things are copied. So when you pass information to a function, it gets copied across. Pass by reference is when you pass something in, you both share that same thing. And if the function alters it, it alters the original that you've got. Pass by value means you give them a copy. Pass by reference means you give them a reference to the original thing, and you can both access the original thing. So this is called pass by reference, pass by value. Well, pass by value makes a lot of sense, but pass by reference, which I've been poo-pooing up until now, and we've looked at how to do it, it does have some advantages. Why might you pass by reference? Why might you not want to do that copy? Yes?
Let's say you've made a game and you've got an object or something that's a big character. Instead of like copying the whole character across, which might be memory intensive,
Yes.
we just point to the character instead.
That makes sense. What he said was, the example he gave was a game. I'll even use your example. It wasn't the one I was going to use, but it's better than mine. Suppose you've got a game, and in this game there are entities. I haven't played a computer game for a long time. Someone tell me a random computer game. Pac-Man. Oh man, you're from my generation. Okay, Pac-Man needs to remember what colour he is, what sort of teeth he's got, which direction he's heading in. There's a couple of bits of information that Pac-Man means to know. You might want to call a function and pass it the information about Pac-Man so the function can work something out, like did he just manage to gobble the fruit in time or something like that. You've got a did you gobble the fruit in time function. So you need to pass all the Pac-Man information in. If the Pac-Man information is a whole lot of information, passing it in, doing that function call is very expensive because it all has to be copied into the stack frame of the other function. Then the other function uses it, then it all gets thrown away. You were thinking of a more elaborate game maybe, which maybe the thing you're trying to pass in might be a megabyte worth of information. The thing needs to be able to scan over and get some of that megabyte worth of information, but it doesn't need much of it, it just needs a few little bits of it. It's a real pain if you have to copy the whole megabyte into the function, then the function runs, because that wastes time. And actually there's a downside of that, because programmers start not wanting to use functions then. They start saying, this function call is too expensive. I'm just going to do it in main. And they make their main bigger and bigger and bigger because they don't want to have functions because functions are too expensive. And that's a disaster for your program. You don't want a big main, it's complicated, it's not going to work. You want to break lots of functions and get all the advantages of functions. So pass by reference lets us pass big chunky objects down without having to copy them. Now in C, you haven't seen many big chunky objects. You've seen ints and doubles and floats and chars. They're tiny. Who cares whether they're copied or passed by reference? You have seen now one big thing. What is that? Arrays. An array, you could make an array that's contains 1 million elements. Each of those 1 million elements might be, I don't know, might be an int, 1 million ints. So that's 4 million bytes, say, if you've got 4 bytes ints. That's a huge thing, 4 million bytes. You want to pass that array into a function, do you want to pass it by copy or pass it by reference? You probably want to pass it by reference, because that probably is too much of a cost. Now in a decent programming language, and I'm not here slagging C, but in a decent programming language, the programmer would be faced with a choice. And the program would say, oh, in this case I want to pass it in by reference rather than by copying, because it's going to be too expensive to copy it in. C took a different path. C said, if you've got an array, I reckon you always want to pass it in by reference. So C always passes arrays in by reference. And how it does that is a little trick that Tim mentioned to you, that whenever you pass an array into a function, suppose you've got an array called, I don't know, the heights. Heights is some array. If you wanted to pass heights into a function, and you said, I don't know, call task on heights, that's my function call, C automatically replaces that with a pointer to the first element of the array. And it doesn't attempt to copy it, it just copies the pointer in. And anyone inside the function that accesses the array is accessing the original array, which is sometimes good and sometimes a pain, because sometimes you actually want to give someone a copy of the array. For example, if we were writing a game and you were writing a player, and you were writing a player, and you were writing a player, and I wanted all your players to interact with each other and play, and all the game state was stored in an array, and you guys needed to see the game state, if I gave you each a reference to the game state, what could their functions do? They could fool around with the game state. I say, here's the array of all the information about the game, promise you won't change any of it. And I go, oh sure, yeah. Just give it to me, I'm the player. Oh, by the way, I've got 900 lives now, and oh, where's he hiding? I'll just look in the array, oh, he's hiding there. And they get access to everything. That's a real pain. You do often want to compartmentalize information away from your functions. You don't necessarily want to give them the whole thing. You don't necessarily want them to be able to change the original thing. When I give you a transcript, it's passed by coffee. You go up and pay $5 to get a uni transcript. That's a copy of your transcript. It would be insane if I gave you the actual pointer to the uni transcript database pointer thing and said, here's your transcript. Don't change it though. Okay, does that make sense? Yep. Okay. No. It's sad, but there you go. Okay, so we've seen passing arrays. So that's all the revision I wanted to do. Now where are we up to? We've still got a quarter to the hour. So I wanted to show you this really cool magic trick. Because while I was in Hong Kong, I was trying to teach myself magic, because I think magic is very cool. So I got a magic box and a magic wand, and we're now going to do some magic. Is everyone ready for the magic? Pull 200 Mars bars out of my pocket. I don't know what you're talking about. Now here we go. Okay, go. Go. Oh, no. It's not working. Oh, my mic fell out. Oh, everything's not working. Sorry, guys. We've had a technology breakdown. You go here, you go here. Ta-da! Thank you. I make a document camera disappear. Its usefulness disappear. All right, I'm gonna need a volunteer to check I'm not cheating because I'm not going to be able to do it on the document camera. Can I have an impartial volunteer? Oh, me. Okay, Richard, you can be the impartial volunteer. No, hang on. People might suspect that. You told me. Don't tell me, Ritika. Come up here. Come up here. You can be the scrutineer to make sure I'm not going to cheat. All right, now I've got my magic wand. Ooh, it's highly magic. It's also silver. I've got my magic box. Inside the magic box, I have some magic cards. I'll put 3 of them out here. All right. Is it Ritiksha or Ritika?
Ritika.
Ritika. Can you tell everyone what's on the 3 cards?
Right.
Tell them the names of the cards.
A 4.
The 4 of
Diamonds.
diamonds. 4 of diamonds.
And ace.
The ace of spades.
Spade, yeah.
The ace of spades. No, that's fine.
What do you call that?
The queen of hearts. The queen of hearts. Okay, does everyone remember? 4 of diamonds, ace of spades, queen of hearts. Now, I know which one you're going to pick because you're going to pick one of them. Look, I don't know. The magic wand knows. The magic wand knows everything. Okay, tell me when to stop.
Alright, okay, stop.
What did you stop? What did the magic wand stop on?
The 4 of diamonds.
The 4 of diamonds. Please open the magic box. Show everyone. I glued it in. What is it? What is it?
The 4 of diamonds.
The 4 of diamonds. Thank you very much. Well done. Would you say that is the most impressive magic trick you've ever seen? Do you want to see it again? Okay, I need another volunteer. Saw someone in half. Volunteer from you. Yep. Come down. Okay. Okay. Just check the magic box is ready. Okay. Tell me when to stop. Now, you sure you didn't want me to stop on the 4? No. Okay. What's your name?
David.
David. Turn over the ace of diamonds. Clubs. What does it say?
You will pick me.
Turn over the other cards. What do they say? Nothing. The only card that said you will pick me is the card we picked, the ace of spades. Thank you. Now, a good magician never reveals his trick. But do I want to have a 3rd volunteer? Yes, please come down. Oh, can you get down? Okay. Okay, tell me when you want me to stop.
Ooh, somewhere around the Queen of Hearts.
Take my magic wand, turn it over. What does it say? You will pick the queen. Thank you. Thanks very much. Now, this is a demonstration of what I like to call make sure you get the spec well in advance and get it pinned down. Because if someone is free to change the spec, if they're free to change the parameters of the problem, you're doomed. You must get them to commit to the problem you're trying to solve before you try and solve it. Yes? So when do you get task 2? Oh yeah, look, we will get task 2 soon. We're going to have a break in 5 minutes, and I wanted to do some quick stuff over the break, so you guys got to help me. I have this idea that we would demonstrate the use of arrays. I'm now going to do a little bit of array work. And I thought rather than just sort of talking about arrays, we'd write some code. 2D arrays, like a grid or something. What's that? Make a game? Do Pac-Man. I want to do something we have enough time to write in class. So text-based Pac-Man, while being awesome, wouldn't be any good. So I want a game. We could do it in a grid. Look, a grid can also be represented as a single array. You haven't seen grids. I don't necessarily want to... Well, let's do a grid-based game. Okay. Can anyone think of a simple grid-based game or a puzzle, like a crossword or something like that? Chess. Chess might be... Noughts and crosses is good. Who wants noughts and crosses? Any other guesses? Sudoku. Who wants Sudoku? Oh, how come? Why the interest in Sudokus?
Because 1911 has to.
Oh, 1911 has to do. Oh, okay. All right. Let's do Sudoku. Shh. And promise we won't tell 1911 anything we do. Okay. So in the break, I'll set it up. I'll start writing the file. That's why I wanted to do it before the break. And then when we come back from the break, we'll write a Sudoku. What? You want something that plays the game? Something that solves the game? A solver. We'll write a Sudoku solver together using arrays after the thing. Okay. Now, shh. Before we take a break, you're just about to have a break, but hey, guys, shh. No trip is any good without presents, so I brought you some presents. And so I would like, if everyone could come down and just take one of these. I have 256 Mars bars in here. So if everyone could just come down and take one. They're from Hong Kong. But amusingly, you should have seen me take them through customs. Amusingly, they're actually made in Australia. Imported to Hong Kong, but you can see, look, that is definitely Chinese. Yeah, it's definitely from like a Chinese shop, but... Okay, so go. Can everyone please take one? Just take one, because there's only enough to go around for one each. Thank you.
Task 2 possibly be a Sudoku solver? That's a reasonably hard task to do.
Oh, no, it's trivial. We'll do it. We'll knock it over in the lecture. Yeah.
With all things possible?
Yeah.
What, brute forcing?
Oh, well, you wait and see. Let me think about how we're going to do it. I need a couple.
An exam question from UNSW that like those computer question things. That was meant to be the hardest question.
Which one?
I think 2005 UNSW high school question. That was the finals final question.
Oh, the 2005
I
one.
think it was 2005. Yes.
I wasn't doing it in 2005. I think I stopped in 2004. So it would have been someone else.
Yeah, but...
So I don't know those questions. But yeah, sure, get me some of those questions. I'll set them. Sure.
Oh.
But we'll do this now. Yes.
Just wondering about when you had the...
Yeah, do you want to come over in here? We'll have a look.
I've been programming for a bit.
Yes.
But like you mentioned, I usually have the stars next to these because of type.
Oh, yeah. I mean, that's how Pascal works, but that's not how C works. C plays this game that this expression evaluates to that. And now, the reason, I mean, C will forgive you. If you put the star over here, it just thinks, oh, you put the space in the wrong spot, and it just moves it across for you.